Okay. So as we were discussing, that it should follow the criteria of finding out the symmetry element. If it is falling into the criteria, irrespective of what kind of ligands it is having, it would be having that inversion center. So I hope this is quite clear to both of you. Now we will move to the another symmetry element, which is improper axis of symmetry. So first one which we read, that was proper axis of rotation. This is improper of proper axis of rotation because it consists of two elements together. So it is rotation about an axis, which is your CM, principal axis, and followed by that, it would do the reflection operation through a plane which is perpendicular to your CN axis. So it is having both two elements in this particular symmetry operation. It is having both Cn dot sigma. That means either you apply reflection first and followed by rotation, or you can do sigma dot Cn. Whenever you see this multiplication, you always have to first apply the right hand operation, then you apply this one, right? Now, in this case, both of them will give you the same result. Now, if you consider this molecule, a very known example, methane molecule. So methane structure is, so you have this methane. We are considering this as HA, this as HA, this is B, and this is B, this is HA. So here the two HA are in plane.
Just wait, Connie.
Sorry. Reem, you have any question?
No, ma'am, sorry.
Okay, sure. So HA, we are considering HA, which are in plane, and both HB, one is out of the plane, one is above the plane, and other is below the plane. So we just name them as out of plane hydrogens, right? Now, whether it is having an improper axis of symmetry or not, I'm giving an answer. It is having a S4 improper axis. So this is an S4. The symbol of improper axis is SN. It is defined as Sn, right? And Sn is having, say for example, if I'm saying S4, that means it should be having C4 into sigma. If it is S5, I'm saying C5 into sigma. That means C5 is your proper axis of rotation, principal axis element, and followed by the reflection. Now, when we know, I am saying that whether it is having S4 or not, it should follow this particular uh, formula, which is C4 and sigma. Now, what we will do, firstly, we will rotate it by sigma, as I have written. So we will first give an operation of sigma, that is a reflection. Now, if I'm considering, you have to be very careful. As I said in this definition, the rotation about an axis, when you're defining an axis, say for example, you define the axis as Z, the rotation is happening on the along the Z axis, then the reflection has to be through a plane which is perpendicular to it. If I'm taking Z axis, then plane is sigma xy. If I'm taking axis as x, the plane would be yz. If it is y, then it is xz. If it is z, then it is xy. Is it clear? Is it clear?
Yes, ma'am.
Okay. So now here I am giving a concept that I am talking about S4 along the Z direction. That means C4 is along Z direction, and perpendicular to this sigma, perpendicular to the Z becomes XY. Okay. Now considering the C4Z passing through your carbon, considering a C4Z passing through your carbon, so we are expecting to have a sigma XZ. Now, when I'm taking a sigma XZ, it would be passing through a plane, and the plane would be having this planar thing. That is why I said The two hydrogens which are onto the plane, they are defined as HA, and the other two are out of the plane, right? So this plane would be having sigma XY plane would be having both the hydrogens onto that particular plane, but HBs would be out of the plane. So what do you expect? What it would become? Hello.
I can't understand the question.
Okay, I'll just make it more clean. So if I am having HA, there is carbon, this is HA. Even though I'm making it in a square planar kind of geometry, consider it as a tetrahedral only. For making you understand more, I'm just making like this, right? So here I'm saying the C4 will, so this you can see it is in plane. C4 will pass through the carbon, which is a Z axis. But firstly, we are applying this C4, where we will be getting, we are having a C4 Z axis. So what would be now your configuration? So this hydrogen C4 is nothing but your 360-degree divided by 4, which is your 90-degree rotation, right? I am saying n equals to 4, and we know n is equals to 360 by theta. So theta when goes here, n goes down, it gives you a rotation of 90 degrees. When you have an HA in plane, when you give a 90-degree rotation, it becomes out of plane, right? So now this HA would be here, but it becomes above the plane, and the other HA would go below the plane. Since this was out of the plane, after 90-degree rotation, they come onto the plane. So therefore, I'm giving it a solid direction. And when this HP above plane goes to the 90 degrees, having a rotation of 90 degrees, it comes in the plane and therefore it becomes like this. Now, what we started with, the bonds were onto the plane here, they became out of the plane, and the other two which were out of the plane, they became in plane. After this, C4 we have applied. Now you have to apply a sigma XY, the plane reflection that we have to do. Now, when I am putting, since this was my Z direction, so this becomes my plane. This is Y and this is X. Now, when this becomes a plane, remember that this is your out of the plane and this is your below the plane. So when I've put a plane over here, what do you expect this HA to become? It would get reflected to this particular position. And ultimately, we ended up having these HBs would go to this side and HAs would come to this side because they are out of the plane. So this configuration, we started with HA. After giving a rotation, it was HA, carbon, HB, and HB. Now, when the plane is here, because this was the Z direction, this is your XY. So when we are giving XY, which is perpendicular to your C4Z axis, they get reflected to each other, and therefore we ended up having HB above and HA down. So this is your molecule, final molecule B, and this was your initial molecule A. So what do you think that initial and final are the equivalent? So initial molecule are having both the bonds in plane and the down bonds out of the plane. Final molecule also is having both the bonds in plane and down bonds out of the plane. So are they equivalent?
Yes, ma'am, they are equivalent.
Sorry?
Yes, ma'am, they are equivalent.
Yes, they are equivalent. Right. So even though this S4, you need to go back to more examples, solve more examples to get to know more about the improper axis of rotation. The take-home message is for improper axis of rotation to happen, it should, it is not recommended, or it is not compulsory to have both the elements C4Z also and sigma also in the same molecule. These elements could exist, these elements could not exist in that particular molecule, but ultimately after giving both the operations, we should be having an equivalent configuration, and therefore we say CH4 is having an S4, the improper axis of rotation. So this element is present in this particular system. And the last operation that we have is our identity operation. So identity, as we said, that if we are starting with H1, H2, if I am giving C2Z, it would give me H2, oxygen H1. But if I am giving it C1, so what do you expect it to be? What C1 means? What is the theta value?
360 degree.
Right. So this is 360 degree. 360 means it would come back to its original position. So this we call as equivalent, and this we call as identical, as explained earlier. And therefore, this particular operation is called as E. If it is giving you an identical configuration, that is called as E identity operation. So I hope this is clear to you. We have already, so these are the main symbols that you need to remember. One is Cn, another one is sigma, which is divided into three parts: sigma H, sigma V, and sigma D, followed by you will be having inversion center, then Sn and E. So Sn is not, Cn is nothing but your proper axis of rotation. That means you need to give a certain angle of rotation along a particular direction, and n is equals to 360 by theta. Sigma is your plane of reflection. Sigma h is your horizontal plane. Horizontal plane is something which should not possess your principal axis. Say, for example, as I said, if my molecule BF3 is having principal axis of C3Z along the Z direction, that means sigma xz or sigma yz can't be the horizontal planes. They can be vertical planes, because vertical planes should possess the principal axis of rotation, right? And sigma d is something called dihedral planes. This I will explain you in coming classes. This would even further confuse you. Or just to give you an example, if we have two C2s, say for example, C2 is coming from here, this rotation is C2. So in between the two C2s, the plane that exists, that is called as dihedral plane, that I will explain you example in next session. Followed by we have this inversion center, which we have seen in many examples. This we just talked about, improper axis of rotation, which should be, which comprises of both C and Z and perpendicular sigma. This can be Z, it can be X, it can be Y, depending on your plane would change. And this is your identity operation. So is this clear? Any doubt in this particular thing?
No, ma'am.
Okay. So at this point, I think we can do the little bit question. Now, can you please tell me that what is the number of proper axis of rotation and improper axis of rotation operations exist in the BF3 molecule? We have already seen, to please try this example. BF3, we have already seen the molecule. Now, first understand the question carefully. Proper axis of rotation, the symbol you should know, this is Cn we are talking about. Improper axis, we are talking about Sn. Now the question says, find out the total number of proper axis of rotation as well as improper axis of rotation operations. So you need to talk about their operations. How many times that uh, particular operation can be made? One time, two times, how many times? So that total number we need to find. Say for example, I am giving you, we know that C3 is exists in particular case of BF3 because after giving a rotation of 120 degree, it gives me identical molecule. But how many times I can do C3? Say for example,
Three times.
sorry,
Uh, three times, no? You can rotate it
okay,
into three times.
we'll just take your example itself. You said three times. That means C3 one, C3 two times, C3 three times, right? Now I am making a BF3 molecule at this side. BF1, F2, F3. Now apply C31 along the boron direction. What would be the configuration here? So I'm writing B, B, and B. Now apply C31, which is what is the angle of rotation here? Team, you tell me what is the angle of rotation here?
120.
Yeah, right. So now rotate the molecule passing through this boron. I'm giving C3 Z direction and rotate it by 120 degree. Now tell me what would be the uh, positions of your F molecule, F atoms.
First, F3,
Hmm.
F1, F2.
Okay, right. Now rotate this one more time. What is C through two, C3
F2,
2? What is the angle of rotation?
F2, 120.
No, C3 2 is your 2 times multiplied by C3 1. So this is 240 degree.
240 degrees.
Right? Or you can say what when you have applied onto the C31, whatever you got C31, you apply one more time, 120 degree. That is also convenient.
Okay.
Okay. So you can't go to this one and apply only 120. That would give you the same configuration. When you have done one operation, if you want to do this C32 can also be written as C31, C31 because 1 plus 1 is 2, right? So one time you have done BH3, you got this molecule, apply C31 again. You will get the C32 operation. So what would be the F positions? What is this
Uh,
one?
F2, F2,
Right,
F3.
right. Now apply C33. What is this C33 theta?
It's 360 degrees.
Okay. So 360 degree will give you what?
Same.
Identical.
Right. So that would give you an identical configuration. When identical configuration is there, what is the symbol of identical? This is the,
E, E.
this is C31, this is C32. What is my question? I asked total number of proper axis of rotation
Okay.
operations. It has to be proper axis. I didn't ask like total number of operations. If I will say that, tell me in BF3 molecule, what is the total number of operations, then I can consider C31, C32, C33, all the operations. What I mentioned is I talked about the proper axis, and proper axis has to be with the symbol Cn. When you did
Yes.
C33, that
C3,
becomes
only one.
identity, right? When you did C33, that becomes identity. So it is no longer a proper axis of rotation. Is it clear?
Yes, ma'am.
So when somebody is asking you how many operations are possible for C3, if I am giving C3, so it can give you two operations, which is C31 and C32, because in each molecule, irrespective of what molecule you are taking, identity is will be existing there. There is no molecule such that it is not going to have identity. So identity is compulsory in every molecule, right? But when we are talking about the proper axis of rotation operations, you need to just consider how many times we can apply C3 on. So C31 and C32 individually they are, because none of the symmetry operations should repeat itself. Say for example, if you will say C31, C32 and C33. I have counted C33 here, which is equals to E. Now when I will be counting the total number of elements, I already will write E, then I will write C31, C32. If I will write C33 again, then this is a wrong situation because we can't count any element two times. So it can be either counted as E or it can be taken as this one. But the question says you have to calculate the proper axis of rotation where identity does not fall. So only two operations are possible for C3. Similarly, if we do for C2, now again you have BF1, F2, F3. Now you tell me how many operations are possible for C2. What is C2 defined? C21 defines theta equals to,
180.
right. So give 180 and what you will get? 180 along what? You need to define because there are three
The
possibilities. Either
axis
you give 180 along this one, or 180 along this one,
or
or
F2
180 along.
or F,
Yeah, right. So if I'm saying BF1, so what would be the change? F1 will stay as it is. F3
F2 and
will go.
F3.
Yeah, right. So therefore, we gave a 180-degree rotation. Now, what will happen with the C22? What would be the theta?
It's 360 and it will be identical.
So we can't consider it. So therefore, C2 will only give you one proper axis of rotation, right?
Yes, ma'am.
Okay. Now another question in this line itself. We said that BF3 was there and 1, 2, and 3. So corresponding, firstly you answer me how many C3s can exist. C3 is passing through boron and it is rotating by 120. I'm not talking about the operation. I'm just asking how many C3s can be existing. Is it one? Is it two? Is it more than three?
Only one can be existing.
Right. So only one because principal axis can only be one. It can't be multiple. Right. And how many operations this C3 can be existing giving?
Two.
Right. And what are those C31 and C32? Is it clear?
C1, C2.
Right.
Yes,
Now talk about C2 because we need to find out all the elements. Now with the C2, how many C2s are present in your molecule?
three C2s.
And all the C2s are along what? Along B and F bond. Since we have
B and F.
three different fluorines, so it would be one C2 would be along the BF1, another C2 would be along BF2, and third C2
BF3.
would be along BF3. So we will be having three in number, but how many operations it can give?
Only one.
Okay.
C2
So
one.
now you tell me total number of proper axes of rotation is possible in your system. How many proper axes it is giving?
3.
See, uh, if one is giving one, say for example, C3 is only one in nature and that is giving you two,
1. One.
right? So
2.
it would be having two coming from C3 and one C2 gives you one operation. Three will give you how many?
1.
Three C2s will give you how one?
3. 3. 3.
Right. So 3 into 1, it would give you 3. So 2 plus 3, how many?
3.
5. So therefore,
5.
when I've asked the total proper axis of rotation operations, that is 5 in number. This is how you calculate. So in BF3 molecule,
Okay.
you have one C3 and three C2s. Is this clear?
Yes, ma'am.
So what would be the C1? Since this is the maximum principal axis that we can have, we are going from maximum to lower. We went from C3 to C2. Now, what would be the C1? Why are we not considering C1?
It's identical operation and it is not
Yeah,
a
because
proper axis.
right. So it is actually been already taken, and that is not a proper axis anymore. It becomes an identity that is E. So we don't consider
Yes.
this at. So whenever the if total operations are being asked, then you have to consider each and every element. But if only proper has been asked, then you have to consider the proper one only, right? Which are individual. Now, this was the half part of the question. The second part of the question says you need to found that how many improper axes of rotation present in your system. Now, the question is, firstly, you need to identify what is the SN value that can exist in your system, right? So, say for example, I am saying that in this particular BF3 case, we have S3. Just consider if S3 is possible here or not. So when you have S3, what S3 means? Sn is equals to Cn into sigma, which is perpendicular sigma, right? So S3 becomes C3 into sigma. Now we need to find out how many individual S3 operations are there. What we will do, we will take a multiple of these things until and unless we achieve the identity. The similar way we did it for the C3 and C2. Until and unless it stops at this, we stopped at C2 itself because it achieved the identity. We stopped at C3 because it achieved the identity. Similarly, in S3 also, you have to do a multiples of it until unless you reach the S3 identity. Say for example, if I'm saying S31, S32, S31 is C31 and sigma one time multiplication you have to take. Now, if I'm saying it is along the z-axis, then sigma would be along xy. This has already been cleared, right? Now, C31 and sigma x1, you need to apply this confirmation. I'll just show over here. If I have VFP like this molecule, and I said that this is my x-axis, and this is my z-axis. And these were already, I considered them onto the plane. So they are in the plane of xy, right? Now, firstly, I'm applying the right hand side operation, which is sigma xy. What do you think would be the configuration now? So plane can do one thing, two things. Firstly, they can reflect. If their reflection is not there, then they will bisect. So in this particular case, when all the atoms are onto the plane, are they reflecting or they are bisecting?
Bisecting.
Right. So none of the places will be moved. They will at the same places, but I am giving a symbol of this circle, which is dashed one. This is reflecting, that is just bisecting. This is the normal molecule. Understood? Now, after this is applied, now what you have to apply? You have to apply C3Z. C3 along the Z direction. Now, pass the Z direction along the B, boron. What do you expect to have your molecule? Where the F1 will go or whether it will go or not.
It will move.
So F1 will come here,
There. Yes,
right?
sir. F2
So
will
F
go there.
yeah, F1 will come here, but the that particular bisecting is still happening. F2 will come here and F3 will go here. Clear? Right?
Yes, ma'am. Clear.
We started with A, we ended up with B. What do you think A and B are equivalent?
Ma'am?
They are equivalent?
Yes, they are equivalent.
Right. So that means this exists, right? So C31 and sigma x1, that is an individual operation that is not giving me anything, any other operation. So S31 is existing as an individual. So one operation is done. Now consider, draw in your notebooks S32. Apply S32, which is equals to C3 two times along the z direction and sigma xy 2. I would just give you a thing. Whenever the sigmas are in even number multiplication, that tends to give you an identity, right? And if they are in odd number, that would give you a single sigma point. You can try by yourself. Now onto the same system, apply C3 two times, C3 2 and sigma xy 2. So this becomes, say for example, if I am taking F1 to make you understand this even more better, if I started with this circles, that means onto the plane, after sigma xy, they become bisecting part reflected by this dash. And again, I'm giving sigma xy, right? So after this one, what do you expect? It would come back to its original form. The bisected part would go down and the other part would come again. And this is what? Identical to each other?
Yes, ma'am.
So this becomes E. So this part we don't know. We don't even consider that. Only then you have to see when the S32Z was equal to C32Z and sigma XY2. This becomes C32Z and identity. Anything multiplied by identity gives you same thing, that is C32Z. Now I started with S23. I ended up having C32. This is improper. This is proper. Will you consider this particular improper axis of rotation operation in counting?
You can consider E.
See, what I said is, if I was talking about LCN operation, so when I was doing C31, so this was an individual operation. C32 was an individual operation. C33 was equal to something else. So this can't be a proper axis. That was clear,
Yes, ma'am.
right? Now, consider the S31. S31 is C31 and sigma, both are existing. So this is an individual operation. S32 is becoming C32 and E. Sigma square is E. So this becomes C32. This has changed. This is no more a improper. So this can't be counted. Now take SC3. This is C33 into identity, into sigma 3. Now C33 is what? Identity.
Identity.
And sigma into sigma 3 times, if you will just do a calculation, sigma 2 is identity again, and this is sigma, right? Anything multiplied by identity would be the element itself. So S33 is your sigma. So this is also not improper. This is also not counted. Okay.
Okay.
Now
Only
go
one is
further.
counted.
You understood?
Yes, ma'am. Only one is counted.
Okay. So S34, no, not only one. You have to go until unless this value becomes equal to identity. We stopped here when C33 was E. We stopped at C2 when C22 was E. So you cannot stop at sigma. You have to calculate the multiples until unless you reach the identity, right?
Identity. Okay, ma'am.
So S34,
Okay.
what it would be? It would be C34 and sigma 4. Sigma 4 we don't consider because this would be identity. It's an even number. Now what it would be? It was C34. Again, this can't be counted. So far only one was counted. Now calculate S35. S35 is C35 and sigma 5. Any odd number of sigma would be sigma. If you'll just do like this. 2 square into sigma, and this would be sigma, right? What happened to C35? C35, if you will say, it would be actually C32. It is nothing but if you will write it like this way, right? If you will just see like this is nothing but a multiplication of C32 and C33. C33 is what? Identity. So what we ended up having C32. So this is C32 into a sigma. So still this particular operation is not there. So this is an individual operation. So this exists. This will be counted. Okay. Now the last one, because this is the definition of your S. Sigma, proper axis should also be there. Sigma also should be there. And lastly, when we have C36, now you count C36 and sigma 6. Sigma 6 is sigma 2 into sigma 2 into 2, which is an identity. And C36 is nothing but your C33 into C33. What is C33? That is identity. This C33, that is identity. Sigma is already identity. All the multiplication of identity gives you identity. So this is 36 becomes identity. So now you stop at this point,
Okay, ma'am.
right? So out of, we came up to 6 operations, but out of all of them, only S31. So if we'll just write in a summarized manner, so our S31 exists because this was a combination of C31 and sigma. S32 becomes C32. So this can't be counted. S33 becomes sigma. That is also not counted. S34 becomes C31. That is not counted. S31 was C32 into sigma. So this is counted. And S36 is identity. This is also not counted. So therefore, S3 is giving you 2 operations, which is S31, S35. Two improper axis operations, I would say.
Yes, ma'am.
Is this
Thank you.
clear?
Clear, ma'am.
Okay. So I think we are only left with 7 minutes to end up this meeting. I would share this particular presentation with you guys, and there are certain questions. Question two, there are 6 questions, but with proper examples. I would suggest you to just go back and try to solve these questions by your own. And we will be taking half an hour to explain these questions, proper explanation in the next session. And we will continue to discuss about the week two lectures. Is that fine?
Okay.
And
Okay,
before
ma'am.
ending, I would like to ask you, is there any problem you faced during the session, or is there any doubt you guys are having? Please let me know. I can still take 5 to 10 more minutes to explain your doubts. Whatever you are having doubt, you just let me know. We will finish it off here itself.
Everything is clear to me.
Okay. So I'll just give you a proper brief of what we have done. This is a summary, what so that you should, whereby when you are preparing for exams, the summary would more than sufficient. So what we have, only one part is left, which I have to take today, but we will continue it next time. What we started with, since we were talking, our first topic is circular dichroism. So this is related with the chirality, as I mentioned. And chirality is related with the symmetry. That's why we started and we are reading more about symmetry. And this chapter is going to be helpful in all of your any syllabus if you will find. Everywhere symmetry plays a very important role, and those who understand the group theory well, they are able to solve any problem. So that is out of experience when I am in IIT, so I can relate how what kind of questions comes and where you can utilize in your research or in any part. Anyhow, so this chirality and symmetry. Then we read about what is symmetry, a little basic of it. Then we related it with energy, and we also talked about the mathematics of it. The mathematics is nothing but we are talking about the operations and the entities. We learned little about the chirality, just the basic example. This we will take in details in the coming sessions. So in energy, we found that higher the symmetry, lesser is the energy, and there would be degeneracy, more degeneracy. That means they would be equal. When you reduce the symmetry, energy increases and degeneracy is lost. In mathematics, what we found, we talked about symmetry operations, and symmetry operations contains rotation, reflection, and symmetry elements that we talked about, that is having that entities that we say that axis or it is line or it is plane or it is point, something like that. Now, ultimately, when we talk about the symmetry elements, we talked about Cn, we talked about Sn, we talked about sigma, which is having 3 parts, sigma h, sigma v, sigma d. We talked about identity, we talked about inversion index. So all the group theory will be revolving around these elements. So this is the only one which we are going to talk again and again about, and your basics would be even more improved. So to practice properly, I would suggest you to go to this site, Symmetry Autobeam, which I just showed you. This particular site link, I will put it in this presentation itself, and that you have to go and practice. There would be a lot of examples, different molecules, different point groups are there that would help you to imagine more, which we can't imagine no easily. You can imagine easily by looking at actually how it is moving, how the plane is doing its job, and so on and so forth. So I've copied the link here itself. So you can just click over here and then you will be directed to that particular site. So I hope this is clear. If there is any doubt, you can ask me now itself. If not, then you can always welcome. You're always welcome to ask question in the next session.
Okay, ma'am. Thank you.
So with that, I would end this meeting here and wish you all the best. Please